Hello there, my name is Jacob Bumgarner, and today I'm going to be sharing with you VesselVio, an open source application I've built for vasculature dataset analysis. To start, I'd like to thank you for checking out my talk, and thank the I2K committee for giving me the opportunity to share my work. In this brief presentation, I'm going to give a bit of a background on my motivation for building the app, give a brief app demo, describe new approaches I've taken, and then finally highlight some example analyses that I've conducted. So, I'm a graduate student working in Randy Nelson's lab at West Virginia University, where we research the effects of circadian rhythm disruption. As part of my work in Randy's lab, I study the effect of circadian rhythm disruption on both pain behavior and cerebrovascular structure. To analyze the datasets that are generated in my research, I get to use a number of interesting techniques and open source tools. Specifically, it was through our vasculature research that I was inspired to build VesselVio. In general, vasculature dataset analysis occurs in 4 stages. First, datasets must of course be created through techniques such as corrosion casting, and then imaged or scanned using tools such as micro-CT scanners. Then the vasculature must be segmented from the imaging datasets. The segmentation then enables us to isolate and extract features from vascular volumes, which finally must be analyzed and interpreted. VesselVio specifically focuses on the third step of this pipeline, which is feature extraction. So why did I choose to develop VesselVio? Well, as I used some of the tools available for vasculature analysis, I noticed that there were several pitfalls. For example, many open source tools rely on outdated analysis techniques, which can lead to inaccurate feature reporting, and some of these tools can also be quite difficult to get set up on local environments. In contrast, many paid tools often provide easy setup and user-friendly interfaces and provide much more robust feature output. However, the high costs and proprietary techniques associated with these tools can often limit widespread accessibility. It was for these reasons that I chose to develop VesselVio. My goal was to create an accessible and open source application that would address some of the pitfalls of previously existing tools. Next, I'd like to provide some brief demonstrations of how the app can be used. First, because I think it's highly important to be able to visually inspect and confirm the results that the app produces, you should always load example datasets for visualization. During the visualization stage, you can select the analysis parameters just as you would on the analysis page, and then the dataset will be analyzed. The results from this analysis will be used to generate meshes for visualization and inspection. During visualization, you can examine different features of the dataset using various color maps. You can also examine and inspect the location of branch and endpoints to refine segment pruning and filtering parameters. Further, you can visualize the original input volume or the corresponding smoothed input volume to confirm that the analysis and reconstruction was completed successfully. Lastly, the result can be inspected as both centerline traces or S-scale results as seen here. After you visualize some example volumes and are happy with the results, you can then run batch analysis on your datasets. Here I've loaded 5 datasets with their respective annotation volumes, and I've created and loaded an annotation file that will analyze 17 labeled regions. To prepare the analysis, I'll configure my input options, and then in addition to the main results file that the app produces, I will also select the option to export individual CSV files that contain detailed information about individual segment features. Lastly, I will export individual GraphML files of the resulting datasets for subsequent analysis network options. Lastly, in order to analyze annotated datasets, we can create annotation files that will specify which regions of interest should be analyzed. Here I'm going to select 3 CA field regions, the dentate gyrus, and numerous parent regions of the isocortex of the mouse brain for analysis. You can also create new ROI labels for manual annotations created in tools such as Slicer or I2K Snap. We then export this annotation file, which will later be loaded during analysis and visualization. Now that we've seen a bit about how the app can be used, I want to dive into a few of the new approaches that I took in the analysis pipeline. These results are described further in our recent publication in Cell Report Methods. VesselVio's analysis pipeline follows the same general stages as previous techniques, but there are several new analysis approaches that I took and pipeline optimizations that I implemented. Rather than focusing on the details of the optimizations, today I'm going to focus in on two of the new approaches that I took during the analysis. In the first new approach, I sought to address the issue of spurious branch point labeling that occurs in naive skeleton-based analyses. In order to identify branch points in datasets, the current main approach is to create an undirected graph of the volume skeleton. Individual nodes of this graph that have more than two neighbors are then labeled as branch points. However, by using this approach, what commonly occurs is that multiple branch point labels are often placed at single branch point junctions. This can be seen by these three red points. This approach artificially elevates branch point counts. Here, for example, we have one ground truth branch point, but the current feature extraction would tell us that we have three. In order to properly analyze datasets, we must resolve these spurious branch point labels. There have been several previous approaches that attempt to resolve these labels. For example, Palagi uses parent vessel hierarchy, Chan uses weighted connectivity, and Kirst and Valkley both use point reduction typed corrections. These approaches work well for simple branch point clicks and click clusters, but in reality, there are many more derivatives and variations of spurious branch point clicks and clusters of these clicks that present naturally in datasets. Rather than only targeting the first type of click for label resolution, I created a generalized approach that targets all forms of these clicks and clusters of clicks. This approach first iteratively resolves and simplifies simple clicks, and then it resolves large clusters of these clicks. The exact steps of these filters can be found in the supplemental methods of our publication. Importantly, through this approach, VesselVio is able to accurately resolve and report the number of branch points present in datasets. Using a ground truth dataset, we are able to report a 97% correction accuracy. In the next new approach, I sought to improve the radius analysis of at-resolution vessels. Previous approaches find the radius of vessels by calculating the distance from the vessel center to the center of the non-vessel nearest neighbor. This approach works well for large vessels, but inflates the size of small vessels, as seen here. In VesselVio, this distance calculation is slightly modified, enabling the analysis of at-resolution vessels. Briefly, a half-unit distance correction is applied to non-vessel neighbors situated at the edge in 2D or face in 3D space. These corrections aren't applied for other types of neighbors. Through this modified Euclidean distance calculation, VesselVio is able to distinguish the presence of at-resolution vessels. Moreover, the resulting shift in vessel size reporting only occurs in small radius vessels. Next, for those that might be interested, I want to provide a brief overview of the app's architecture. VesselVio was built entirely using Python and relies on a number of amazing open source packages, including NumPy, iGraph, and PyVista. The app can be used from the terminal, but it can also be downloaded. Downloads are bundled using PyInstaller and are distributed using SourceForge. Of course, the source code will always be available on GitHub for terminal-based builds. Finally, although I won't spend too much time on the functional architecture, I wanted to highlight the general workflow of the app. Importantly, the backend and front-end pipelines are strictly separated to facilitate future modifications. Lastly, because the app would be frankly useless without the results it produces, I wanted to share some example analyses that I've conducted. First, as featured in our publication, the app can be used to analyze whole brain datasets. These datasets can be loaded with annotation files, such as those provided by the Allen Brain Institute for individual nucleus-based analyses. Next, the app can be used to identify vascular alterations and complications present in various pathological states. Here I use VesselVio to identify differences in vessel radius distributions and vessel segment tortuosities and three types of human retinal vasculature. Lastly, in the context of my own research, I use VesselVio to identify vascular topological alterations in various regions of the hippocampus of mice experiencing circadian rhythm disruption. In conclusion, VesselVio is an app built with ease of use and accessibility in mind, with the goal to democratize vasculature dataset analysis. The app is still being actively developed with several new features in the pipeline and bug fixes occurring as they're identified. Please feel free to contact me with any questions about the app or potential ideas for future implementations. I'd love to hear from you. Finally, thank you for listening.